Hey, Noah, why are you staring at the map?
Oh, I was just looking at my trip for Thanksgiving break. I want to go from Atlanta to New York City.
Oh, nice. But don't you wanna, if you're going all the way there, stop at some landmarks or anything like that? Oxford, maybe.
Maybe. Yeah, I was thinking of stopping by a few places.
That's something related to graph theory, isn't it?
Graph
An
theory?
article?
How so?
Yeah, I think it's K-stops.
So how does my trip relate to graph theory? Well, as you can see here, this is the United States represented as a graph. Each of the states is a vertex, and when they border each other, there's an edge formed between them. When I'm thinking about my path or my route from Georgia to New York, stopping by DC, which is in Maryland, I can represent it as a closed walk or a cycle within the graph, where I stop by different states, ultimately stopping by the 3 states that I need to stop by, Georgia, Maryland, and New York, and ending back at Georgia. We can use graphs like these to figure out what the most efficient path is. This is known as the traveling salesman problem.
So how does K-stop relate to your Thanksgiving trip?
Well, the K-stop distance of a graph is essentially the distance that it takes for a cycle that contains K-specific vertices. For example, my Thanksgiving trip, which involves going from Georgia to Maryland to New York, then back to Georgia, is a 3-stop, where is a K-stop distance where K is 3. This is because I have to go to 3 specific vertices. And the K-stop distance is essentially the shortest path to go to visit each vertice, then return to the original vertice. This distance can be expressed using this quite tedious equation right here, where this equation basically says it's the minimum K-stop distance is the distance to go from the first vertice to the second vertice, second to the third, all the way from K-1 to the kth, and the kth to the first again. This is essentially what a closed K-stop distance is.
Whoa. I'm getting confused. What's D, what's K, what's P, what's theta? What does that have to do with K-stop?
The notation sure is confusing, but the concepts themselves are relatively simple. What P of S means here is every single permutation of paths that can be taken within the graph of S. Theta is a specific path that is taken. As you see, theta is an element of P of S. And as you see, each theta over the equation show one possible path that we can take from a vertice to another. D here means total distance, and K is K means the amount of stops and vertices that we need to stop.
Makes sense. Okay, gotcha.
Okay, so I'm going to explain 3 terminologies that are pretty important in our article. They're eccentricity, radius, and diameter.
Oh, radius and diameter. We learned that in middle school. Is it like the distance between the center and the circle, right?
No, it's different.
Oh,
I'll show you. Okay, so the eccentricity of a vertex means the distance it takes to go from that vertex to the farthest vertex. So for example, the red central point right here, it takes 2 distance to go from this point to this point, which is the farthest. And the radius of a graph is the smallest eccentricity. So for example, in this graph, it will be 2, because obviously the central point has eccentricity of 2, which is the smallest, and the diameter is the biggest eccentricity. So for example, in that graph, it will be 3, and this graph will be 4.
For the second part, we are discussing about the possible value of 3-stop in order to explore more about the K-stop situation. So firstly, we could see that this equation would always establish, because here is a graph about the distance between x1 and x2. So the extrinsic 3 for x1 in this graph will equals to the distance between x and x1, the plus distance between x1 and x2, and plus the distance between x2 and x1. And it also equals to the extrinsic of x1 and extrinsic of x2 as well. So what we are proving is that the radius of 3 in the graph is smaller or equal to the diameter of 3 in a graph G, and is smaller or equal to 3 over 2 radius 3 of a graph G. So how do we prove that? We could by using this formula, which is its transitivity formula. If this fits, I think that this one will also fit. So just like we could change the x1, x2, x1, x2, and x into x, y, and w. So we could see that extrinsic 3y equals to dyw plus dwx plus dxy. It is also equals to extrinsic 3 of x and extrinsic 3 of w. So at this time we will introduce another vertex u. We would make the u follows that duy plus dyx plus dxu is smaller or equals to duw plus dwx plus dxu. And it also follows that duw plus dwy plus dyu is smaller or equals to duw plus dwx plus dxu. So we could see, like, induce another vertex of u here, just like there are other vertex in this, so that it follows this formula. And we could see that these two are the same, so we could balance them by erasing them. And duw and duw is also the same, so we could also balance them. So we could get a final formula that is 2duy plus dyx plus dwy is smaller or equals to 2dwx plus dxu plus duw by plugging them together. So here we are discussing about the first case, which is dwx is smaller or equal to 2duy, and by moving this part to this part, just by minusing it, we could get that E3y is smaller or equals to dwx plus 2dwx minus 2duy plus 2dxu plus duw. And we could find that this part, dwx plus dxu plus duw equals to extrinsic 3 of u. So just by substituting it into extrinsic 3 of u, we could get this equation. So how to solve 2 times of dwx minus duy? So we could use the thinking of the relationship between x, u, and w. So it is very obvious that distance between w and x is smaller or equal to distance between w and u plus distance between u and x, because there's a triangle relationship. And then by our definition, which dwx is smaller or equal to 2 times duy, we could find that 2 times of dwx is smaller or equals to 4 times of duy by just times the inequation of 2. And by adding them together and plus another dwx, we could find that 4 times of dwx is smaller or equals to dw plus dux plus dwx plus 4 times of DUI. This is just adding work. And we could also find that this is another representation of extensively 3 of u. So we could write it in the form of this, and by minusing this form in this side. So 4 times of dwx minus 4 times of duy is equal or smaller than extensively 3 of u. So 2 times is smaller or equals to half of the extensively 3 of u. And here we could get this result. And there is also another occasion that dwx is larger than 2 times duy. We could see that extensively 3y is smaller or equals to 2 duy plus extensively e3u by our definition. And this one is also because by the condition offering here, this one is also smaller than the dwx, so we could write it in this form, and smaller or equal to become too smaller. And E3u is larger than duw plus dwx plus dxu, but it's also a triangle relationship that we could see dwx is smaller or equals to duw plus dxu. So just substituting this part into the whole equation, we could see E3u is larger or equals to 2 dwx. So dwx is smaller or equal to half of the extensity 3 of u. From the very original equation, we could see that extensity 3 of y is equals to dwy plus dwx plus dxy. And this one could be substituted as the half of the extensity 3 of u, and these two forms adding together must be smaller than the extensity 3 of u. So we also get this equation that means the final proposition, because since we have proved that the extensity fits with our requirement, means that the radius must also fit the requirement.
Okay, so in the last clip, Brian explained when k equals 3, which is 3-stop question. And now we could just apply the same thing to 4 stops when k equals 4. And eventually we will get to this equation. So we're looking at a graph, vertices VW, XY, and they all have the same eccentricities, and this is just a part of the huge graph G. This is just a part of the graph, so we could have vertices all over. But the thing is, these 4 points have the same eccentricity. So let's say we have a vertex U right here, and then the distance, the minimum distance, if you connect U to all the other vertices, you'll get the radius of the graph G, and that equals to the eccentricity of U. And then we can rewrite d4 uwxy as the minimum distance of this, which I'll show you in the graph. If you connect u, w, and wx, xy, and yu, and you'll notice that since you're connected uw and uy, the sum of these two would always be bigger than wy. So which you have dwy here, and then if you just apply the same mechanism to the following 2 sets of distances, you'll get that the whole thing is bigger than dwy plus dwx plus dxy. And eventually, if you do the same thing what Brian explained in the last clip, you eventually get to the equation like this.
So finally, we reached into our conjecture by proving 1 and 2, which are we have proven in the previous slides, that rate of 3 is gonna be smaller or equal to diameter of 3, smaller or equal to 3/2 of rate of 3, same as if we take k stop of 4 stop, we managed to find the conjecture where if we take k stop with an arbitrary positive integer of k, the value is going to be k over k minus 1 for a k bigger or equal than 2. Otherwise, it wouldn't be a k stop because the graph is going to have only one vertex, and you can't have a k stop with only one vertex, as it has to reach a point and return to the starting point. And we reached into that conjecture by inserting another vertex u to the k-stop's location. So basically by creating another arbitrary value and plugging into our k-stop and finding into this conjecture where for radius k in the graph g, it's smaller or equal than the diameter of k in the graph of g, which is smaller or equal than k over k minus 1 times the radius of k in the graph of g. And that's our conjecture. Thank you for watching. We're awesome and you know it.